Hi, I'm Sir Joshua Estilo and welcome to my first Lecturette video. In this video, I will teach you how to use my Lecturette and of course to show you the features of my Strategic Intervention Material or SIMS or simply your E module. I will also be sending this PowerPoint presentation at the end of our period. So let's start. So my first lecturette will be about simple harmonic motion. So this will be our first topic for the first quarter of applied physics. So what are the features of my SIM or the strategic intervention material? So one of the features of my SIM is the presence of these trivias. So trivias are just interesting information about the topic, and I hope that you will learn a lot from our trivias and some other important information related to the topic. So one example here is the world's highest swing found in Queenstown, New Zealand. This thrilling ride is an example of objects exhibiting simple harmonic motion. Okay, so let's proceed. So what are the features again of my sim? So you have here the table of contents, you have the overview, the objectives, and of course a review of the topic. At the end, you will have the summary, then the drills and exercises, and after that you can view the answer keys, references, and of course the acknowledgement. So one helpful feature of this e-module is that you can easily navigate it by simply clicking on the following boxes. So for example, you want to view the objectives of our or the summary of our lesson. So just simply click summary and it will lead you to the summary of our lesson. So muna siya ang summary sa atong lesson, and going back to the contents, you simply click on the icon in the upper right to go back to the contents. Okay, so let's proceed. So you have here the overview of our SIM, or also known as the guide card of a strategic intervention material. So here you will learn more about simple harmonic motion, the motion of swinging and oscillating objects like springs and swings, specifically how and why they move. And of course, in this SIM, you will also be given various and engaging activities and exercises that will further aid you in strengthening your knowledge about SHM, or simple harmonic motion. So I hope you will learn a lot at the end of this topic. So what are the features of my SIM? So first of all, you have the lesson focus or simply the objectives of today's lesson. Then of course you have the keywords. These keywords are simply very important terms that you need to know, and I hope that you will actually read the definition of these important terms. So the terms are in a bold font, are highlighted in bold within the text and identified by the keyword icon. So this right here is our keyword icon, the word keyword under a magnifying glass. Next, we have the introduction so that you can be prepared. The introduction sets the stage for the lesson. It may draw upon prior knowledge or briefly describe the organization of the lesson. So you have here an example of an introduction which you will see later on. And of course the lesson proper is where we start discussing the lesson. And in here you will see more explanations about the topics, diagrams, some helpful animations, and of course fully completed examples. Then of course the learning activities. So in this all throughout the module, you will be presented with lots and lots of activities that are fun and of course engaging for you. So next we have the quick facts, or as what I've said earlier, the trivia section, wherein you will be presented with various interesting facts and trivia related to that topic. So that of course you can widen your knowledge and apply this particular new information in your real life situation. And of course you have web resources for additional learning opportunities. So you can simply click this link and it will lead you to the YouTube video that is being presented in the module. So they are identified by the web resources icon. So the web resources icon is simply this arrow key. And of course, these are some examples of my learning activities that are scattered all throughout the presentation of my sim. So you have there the KWL chart, some quick quiz, the PMI chart, and of course the experimentation which you can simply do at home, the materials all available around you or inside your home, the visual thinking map, and of course the drills and exercises. So without further ado, let's start with the objectives of this SHM. So at the end of this lesson, of this 2-day lesson, you will be able to define simple harmonic motion, explain the mechanics of simple harmonic motion. You can solve sample problems, and of course, you need to relate real-life situations to SHM. Simple harmonic motion. Sorry for the typo. And of course, you can share your interest on the activity by discussing it with others or encouraging them to participate. And you can also perform simple laboratory experiments on simple harmonic motion. So don't worry guys, because the materials are very simple. I assure you that I can guarantee that you can see these materials all around you. So you have here your guide for today's sim. We have Albert Einstein. So Albert Einstein will be interacting you all throughout the presentation. So hello there. I am Albert Einstein. I'll be your guide throughout this lesson. So today you'll be learning about simple harmonic motion, and we hope that you will be having lots of fun in answering the activities and of course in performing the lab experiments. So are you ready? Let's begin. So let's start this topic with our KWL chart. So the KWL chart, I think you already know this one. So K stands for know, what you know or already know about the topic, about simple harmonic motion. W for what you want to know. And at the end of the lesson, what you have learned. So this will help you get an immediate background of the topic, making it easier to understand. So I want you to copy this KWL chart on your MS Word file, which I will be collecting next meeting. So you copy this, and you're already given an example of what you can write so that you will have an idea on how to answer the KWL chart. So in this case, I'll be needing four things that you already know about the topic, 4 things about what you want to know, and 4 things about what you have learned at the end of the topic. So again, I want you to write that on an MS Word file and send the soft copy of the file to me next meeting. Okay? So let's start with our topic, simple harmonic motion, a review. So last meeting we discussed about periodic motion. And you all know that periodic motion is simply any motion that repeats itself in equal intervals of time. So for example, you have the sun, our planets that revolve around the sun. It is periodic because it is repeating every 12 months. One example is also the rotation of the earth, or even the movements of the hands of the clock. These are periodic motion because they repeat themselves on a what? On the same amount of time. So one special type of periodic motion is simple harmonic motion, which we will discuss in this module. So let's start with the spring. So as you have noticed, a spring is an example of an object that exhibits simple harmonic motion, because when you compress a spring, the spring will be stretched, and again it will be compressed and it will be stretched, and so on and so forth until it will lose all its energy. So that is an example of an object that exhibits simple harmonic motion. So why is it an example of an object that exhibits simple harmonic motion? It is because it is exhibiting a back and forth motion that is caused by a force that is directly proportional to the displacement. And this displacement centers around an equilibrium position. So you have here the spring that starts its equilibrium position at this point, at 0. So when you press the spring, it will be compressed in this direction, and once released, it will stretch in this direction. Then again, it will go back to its compressed state, and then will be stretched again. So this motion is repeating, causing it to be exhibiting simple harmonic motion. Okay? So you have here Fs of the spring or the force equals to negative kx. So k is the spring's constant and x is the displacement. So take note that it is opposite to the direction of the force. That's why there is a negative sign. So let's have a quick quiz. So which the following best portrays simple harmonic motion? Is it A, a spring moving back and forth, B, moving electric field on a current, C, projectile being launched, D, an apple falling to the ground? So of course the answer is correct. The answer is letter A, a spring moving back and forth. Because you have here the keyword, our first keyword, simple harmonic motion is a motion in which the acceleration of a body is directly proportional to its displacement from the equilibrium position, but in the opposite direction. So when the spring is moving in this direction, the force is moving in that direction. So it is in the opposite direction. Okay, so acceleration is in the opposite direction. So now let's have another trivia. So you have here the Wobbly Bridge, the famous Millennium Bridge in London, in which it is known as the most famous blunders of engineering. So do you know why? It's because during its opening day, the bridge was immediately closed after pedestrians felt unexpected swinging motion. What caused this unexpected swinging motion? This is because of their footsteps contributing to resonance and consequently the oscillation of the bridge. So you know about resonance. Resonance is exhibited when you play the wine glass music on the wine glass. That is also an example of resonance. So let's try to watch more or to learn more about the Wobbly Bridge by clicking on this link. So if you have time, you can still now replay the video. Oh, the video is unavailable. So I don't know why. Maybe they deleted the video. So let's just try searching for the Wobbly Bridge. Maybe it's available on the other links. So right here you have lots of videos about the Wobbly Bridge, and let's try to know why it's called the Wobbly Bridge. So I think this was the first time that the bridge was open. As you've noticed, the bridge is already shaking or wobbling. Let's have it on the screen. So the footsteps cause the phenomenon known as resonance, and this resonance causes vibrations on the molecules of the bridge. So when there's vibration, there is shaking. So as you can see, there are lots of people on the bridge, and the synchronized motion of their footsteps cause the bridge to shake. Okay, so there are lots of videos about the Millennium Bridge, so maybe you can watch them when you have time. So let's proceed. So, let's try to solve a sample problem on Arizona. Close all. So let's try to solve a sample problem on simple harmonic motion exhibited by springs. So you have there Severino Eliote made a spring that needs a force of 3 newtons to be compressed from 40 centimeters to 35 centimeters. What is the spring constant? So in solving this problem, we'll be using the GRS method. So the GRS method is an effective way in solving problems. So what is a GRS method? So the GRS method is a means of solving problem by identifying the given, or simply the numbers that you see here in the problem, the required, or what is being asked in the problem. So in this case, the spring constant, and of course the solution, how you will solve the problem. So let's proceed. So given, you list all the values that are given in the problem and define them. In this case, what are our givens? Let's have the highlighter. So the givens are your force, which is 3 newtons, and of course the displacement, which is 40 centimeters to 35 centimeters. These are your given. So what is being required? So it's simply the spring constant, or K. So solution, we will now solve the sample problem step by step. Okay, did you get the given and the required part of this GRS method? So let's proceed. So by the way, if you find my presentation fast, or you can catch up, one advantage of this sim is that you can simply review or replay this video, and you can simply replay it as many times as you want until you think you get the problem. Or if you have any questions, you can simply write down your questions and send it to me or DM it to me, and then we will discuss it next meeting. Solution. So for the solution, we started with the given. So given F equals to 3 newtons, displacement is 40 centimeter to 35 centimeter. Now, we need to convert centimeters to meters because we are now using SI units. And the SI units, or the base SI units for distance or displacement, is in meters. Required K, or the spring constant. Solution. So one effective way in solving a sample problem in the GRS method is to state the formula first and make sure that the formula is very relevant to the problem, because there are lots of formulas and not all formulas are useful. So F equals to negative Kx. So F equals to negative K, change in X because you change the position of your spring. So probably the spring was being compressed. So X, change of X equals to 0.35 meters subtracted by 0.40 meters, which will give you negative 0.05. Recall that change in X is ng X final minus X initial. Diba the delta is the symbol for change. So delta is X final minus X initial. That's why we are given with 0.35, which is the final, and the initial, which is 40 centimeters or 0.40 meters. Okay, so 3 Newton, our force is 3 newtons. So simply substitute the values, 3 newtons, K, then 0.05 meters for change in X. Substitute the values. Then use the multiplication property of equality to isolate what is required on the left side. So in this case, it is the spring constant. So negative K will be moved to the other side of the equation. So giving us 3 newtons divided by negative 0.005 meters. And that will give you a K, which is 60 Newton per meter. Okay? So Newton per meter is the unit for our spring constant. So again, you can simply replay this video from the start, or in the PowerPoint presentation, you can simply navigate by pressing your arrow keys back and forth, left and right. So pag gusto ka mo. Because I'll be giving the PowerPoint presentation anyway at the end of this video. Okay? So that's how we get the spring constant. So be sure that you encircle or box your final answer later on when I ask you to solve a sample problem. Okay, now let's try to solve. You see, it's so simple, right, according to Einstein. But then you try the next problem. Give yourself enough time before proceeding to the solution. So, sample problem number 2. So, a 21 Newton load metal cube is attached to a spring hanging vertically, and it stretches the spring by 8.3 centimeters. The spring is now placed horizontally on a table and stretched 17 centimeters. How much force is required to stretch the spring this long? So before moving to the next part of the video, I want you to try solving this sample problem on your own, and please pause the video for about 5 minutes. Okay? Okay, are you done? So let's try to check if you are right. So again, remember to try solving the problem first before proceeding to the solution on the next slide. So it will be helpful for you guys if you practice this part wherein you try to solve the problem first before going directly to the solution. So solution, so given again F1 equals to 21 newtons, then displacement x1 or initial displacement, which is 8.3 centimeters, and the final displacement, which is 17 centimeters. So what is being required? That is your F2 or the final force. So remember that the spring began at a vertical position. Okay? Then it was placed horizontally. So you start with the horizontal or the vertical position. So F1 equals to Kx1, 21 newtons equals to K 0.083 meters. So we converted 8.3 centimeters to meters. So that is 0.083 meters. And this one is 0.17 meters. So K for the vertical spring is 253.01 Newton per meter. So what is now the force when it is placed in a horizontal position? So F2 equals to Kx sub 2 equals to 53.01 because we got K, the spring constant of the spring on the previous position, which is vertical, multiplied by 0.17 meters. That will give us the F2, which is 43.01 newtons. Okay? So this is our final answer. Again, you can simply go back to the previous part of this video, replay until you get the solution. Alright, so let's have another quick quiz. So true or false, a swinging pendulum on a uniform circular motion is also an example of objects that exhibit simple harmonic motion. True, A true, B false, or C not enough data. So what do you think? Is this pendulum swinging left and right also an example of an object exhibiting simple harmonic motion? So the answer is true. This is also an example of an object exhibiting simple harmonic motion. Why? If you have noticed, the movement of this pendulum is just like the movement of a spring. And of course, an object moving at uniform circular motion. So we will have a discussion on this on the part 2 of our next meeting. So this will be covered on the next video. SHM and uniform circular motion. So we will try to relate the motion of a spring to the motion of a pendulum, and of course to the motion of an object moving at uniform circular motion or in circles. Okay, so I hope you learned a lot in this video, in the first part of our video, and I will see you on the next meeting.